Very pleased to welcome Daniel Russo, who is an associate, Philip Geyer Associate Professor at Columbia. He's won many awards for his research, including a Lanchester Prize, an Inform's Junior Faculty Interest Group Best Paper Award, and the first place in the George Nicholson Student Paper Competition. Outside of academia, he works with Spotify to apply reinforcement learning and large language models and audio recommendations. And today at our workshop, he's going to talk about posterior sampling by autoregressive generation.
First, I want to say thanks so much for the invitation. Been a ton of interesting talks, and I've been listening very hard, so I'm myself a little tired. So I'm going to walk around a bit and try to stay peppy. Okay, so this is joint work with a bunch of great collaborators. Kelly, who's a postdoc, who's next year joining Imperial College. Tiffany, who's a PhD student in stats, and Hong, who's my colleague at Columbia Business School. It'll be a bit of a different talk. I'm going to be thinking about problems that are related to information gathering and exploration in sequential decision making. And I think it'll be comparatively kind of light on math. And the main thing is a way to kind of tilt your head in a different direction and perceive these problems in a way that makes them more amenable to applying scalable modern machine learning. And so it's mostly an insight talk. Let's see how it goes. A bit of a caveat is, so if you look for this paper online, it's not online yet, and there's some presentation details that are still in flux. So something might be a tiny bit different by the time it is online, because there's kind of different choices of how you might present the same thing. So, okay, very high level here. I am not an expert on cyber physical systems. I really think of digital human interactions as my main kind of motivation. And I interact a fair amount with people who are kind of excited about AI foundation models. And one kind of debate one can have is how much you can learn just passively from the internet. And I think you can learn a lot. Really remarkable, incredible things are emerging. But it's still the case that at least if you have human-level intelligence, then when you go out in the real world, you regularly need to gather new information. Okay? If you have a conversation with someone, if you're a doctor, you ask them questions. And if you're tutoring someone, you kind of probe and understand, try to learn what they understand, what they don't understand. So somehow just a basic part of rationality is knowing what you know, knowing what you don't know and what would be valuable to continue to learn, and thinking how you acquire that information. Okay. So if we're going to really push forward to smart sequential decision making, we're going to have to be able to do that. Okay. So I've often thought of these things that are over on the right, which is about how you comprehend uncertainty and actively resolve it. And that leads you to a world of kind of classical statistics, posterior distributions, latent variables, confidence bounds, all these sorts of things. And if you go talk to machine learning engineers at Spotify, let's say, it's a different language. It's loss functions and prediction and scaling things with transformers and all of this stuff. And what this work is going to be about is building kind of a bridge where there's an equivalent way to view certain classical things. And for instance, in this talk, something like Thompson sampling, which relies on posterior sampling, equivalently in terms of generative sequence model. Okay, so a very different primitive. To make this bridge clear, I'm going to rely on a specific problem formulation, which lets all the insights kind of pop out as almost trivial theorems. Okay. And that problem formulation is going to be kind of like a bandit problem, where you have to explore in order to resolve uncertainty, but it's a meta-bandit problem, in that you face tasks that require learning repeatedly. Okay. Then within that, there's a typo here, we're going to propose a new algorithm, which we call posterior sampling via autoregressive generation. And what that's going to do is train a sequence model just to make predictions. And then within a task, so that's trained across tasks, and within a task, we're going to drive exploration by generating things from that sequence model, taking actions. Okay. And then I'll talk a little bit about theory that justifies that this is actually implementing an already well understood thing in a different way and providing some kind of robustness bounds. And then I'll talk about some experiments at the end. Okay. So related work. This is a tricky thing. Somehow the main insights of this work are something that at some point will come out as fact 1 and fact 2. I give them a proof. The proof I write in quotes. I call them facts. They're sort of just obvious realities. So can anything that's that basic really be new? And in some sense, there's this old equivalence in statistics, Bayesian statistics, between modeling of sequences, the same thing you do with an LLM, and posterior inference. And this is a result of De Finetti. And that's usually not how it was, that's not how it was taught to me. That's not how I understood De Finetti's theorem when I first saw it. I saw it as some result in probability theory. And different people in different communities have kind of rediscovered similar things at different times. There's an interesting view from the causal inference community which talks about estimating average treatment effects by filling in, basically generating missing data. And I never really thought about that as being related, but now I do. I personally was particularly influenced by this paper down here, which is from an old lab mates of mine, which talks about evaluating uncertainty quantification methods in terms of their performance in sequence prediction tasks. They don't actually use this to train methods, but it was kind of through first seeing that I started personally thinking about these problems. Okay. So what is new? I guess I would say one primary thing is this little story and problem formulation I'm going to tell you, which makes the ideas crisp. That seems to be new. Okay. And I think it's helpful that there's a real motivating story. I'm not talking about the thing you usually see of something like God draws a coin and we don't know which bias to the coin God drew. At that point, it's kind of hard to get your head around things. Okay. So algorithmically, we're going to not just talk about uncertainty quantification, but really link this with interactive decision making. And in terms of theory, what's new is we're going to actually go through these approximation type results. In terms of experiments, De Finetti did not work with large language models, but today we're going to kind of bridge that gap. Okay. Behind the times, De Finetti. All right. So let's go into the problem that I'm going to use to illustrate the insights. And as I sort of mentioned, it's a meta-bandit problem. And it's one that's going to require scalable uncertainty quantification methods to do well. Okay. So I'm going to kind of wrap this all up in a story about a recommender system. It's not, don't get lost thinking too much about the details of a real-life recommender system, but this captures a component of the of the major problem faced by a real system, while abstracting away some of the other details. Okay. So the main thing here, they're going to face this kind of recurring problem. They have a user segment. I'm going to think of that as a finite set of people, although very, very big. And for that segment of people, they want to figure out which article is the best one to show them. Okay. And essentially, you know, at the start of some day, not in the control of the system, a big pool of such articles is released. Okay. So pool of articles is released, segment over here, which one's best? Okay. So throughout that day, kind of going from the morning to the evening, they have this process where the articles are released. In a modern system, a large language model will read all of them, and that's somehow, although it's tricky to figure out exactly how to do this, that is somehow going to give you an initial impression of how much each of these articles would appeal to that group. Then, throughout the day, you're going to have sequential interactions with these very large number of people, T people. With each one, you're going to make a recommendation. You're going to see how the person responds. Okay, you might see how long they dwell on the article, see whether they click, whether they like, whether they share. And you roll all of that up into some kind of a reward. Is the system happy or sad with the interaction? Now, there's this fundamental tension here where you're getting feedback only on the things you recommend. So if you don't recommend things at all, you're not going to really get any human feedback on them. Whereas if you recommend things that are bad exhaustively, you're going to get lower rewards. And so there's a tension between exploration and exploitation in this problem. Okay? You can get a feel that it's a little more complicated than a very basic problem in that there's this LLM involved. Okay. So challenges are to, yes, balance exploration and exploitation. If you want to do that, you need to comprehend uncertainty. It's only worth recommending an article if it might be a good article. Right? And that might, in that sentence, is the uncertainty part. Okay. And the thing that makes this kind of a slightly modern formulation is maybe the presence of the LLM right at the start. Okay. Now, the intellectually important part of this is that's one day. But tomorrow morning, articles get released again. Okay. That's going to make a lot of things, that's going to present a major opportunity for us in algorithm design, but I think it's also an important feature of kind of anywhere that exploration really matters in industrial settings. If you only had to explore once, you just do it in a dumb way. It's the fact that this is faced in a recurring basis that it's so important for the system to get it right. Okay. Now again, this is also, I think, something that as academics we don't always feel. That usually an academic runs an experiment, they run it once. But if you're in a big company, you often have scale like this. You have many users, you want to personalize to each user, and so you learn about a person, but you also learn across people. It's a scale that's hard for us to imagine. Okay. So again, there's two kinds of learning in this problem. You want to learn within a day, but because this problem is faced on a recurring basis, you can somehow learn across days. So across your learning tasks, you can learn how to solve the tasks. And that's what the machine learning community is now calling meta-learning. Okay. So I want to explore within a day, and that requires comprehending uncertainty as observations trickle in. And in order to be able to do that well and to synthesize my interaction data in the LLM. Over here, I want to figure out how to draw inferences from data, leveraging data that is acquired across many, many such days. Okay. Any questions up till here so far? Okay. All right, so let's put some letters to the things I've been trying to describe in pictures and words so far. I'm going to call my actions A's, and the little t's correspond to people that arrive, like users you interact with sequentially. So t's are time steps within a day. A sub t is whatever I recommend to the tth user. Okay? Now, when I pick an article, it's going to have two things associated with it, a Z and a U. The Z represents the text and information you can extract from just seeing the text. For us, in the data we eventually use, we just have headlines, actually. Okay. And the U represents the reason you still want to gather human feedback on the articles. Some kind of latent, unknown thing about the article, about how engaging it's going to be. So for any of you who, have any of you seen this silly TikTok video that went viral where a guy rides around on a skateboard drinking a soda? Who's in this? Somehow the U represents that this weird video went completely viral. And it's hard for me to imagine you'd look at a video embedding and know that that was going to be such a hit. You kind of need a system like TikTok that shows it to someone and sees that they can't look away. Okay. All right. Now, so you have the A, you recommend it, it's got some observable and some latent features. You get an outcome, a Y, and you associate that with a reward, R of Y. Okay, so A, Z, Y, R of Y. Now, there's going to be this data generating process, and maybe an essential part of what we do is we make almost no reference to this data generating process. It's in the back of our minds, but the algorithm is not going to like explicitly model these things. In the back of our mind, what we're imagining is that articles are drawn from some article distribution. So if over the past year, every article has a click-through rate of 1% or lower, I just don't expect to see a click-through rate of 90%. Okay? So this kind of expectation reflects that there's effectively a distribution of articles across time that I think is the same. Okay. So that's what this assumption that the articles are drawn from Q is trying to capture. Now, lastly, sort of as is common, I guess, as notation in causal inference or in bandits, I have these things that are potential outcomes. So Y1A notes the outcome of the first time I recommend the article. Y2A denotes the outcome of the second time I recommend the article A. The reason these are potential outcomes is I could choose not to recommend it that many times, and then I'd never see them. Okay. This one? Yes, it's constant across this user segment in a way. I'd say the idiosyncratic effect is that, well, depends how you think about it. The thing that couples, in my mind, your response with someone else's, the thing that to the system means that your response is informative about Alex's response, is that there's a common U to the article. right. So the reason Dufinetti is relevant here is that this sequence is not actually IID, it's exchangeable. It's exchangeable, that's right. Okay. Now, last thing is because this is faced across days, I can go back to everything from across the past year and see historical data on old articles, their headlines, and how much people clicked on them. And that's this dhist, the historical data. All right. So how are we going to solve this problem? Okay. Now, I want to solve this problem in a way that makes no reference to the things, at least directly, that I often do in my own work of posterior distributions and mutual informations, so on. I want that to be more in the background. Okay. So the first step is going to be something which addresses this problem of learning across days. And we're going to train a sequence model to predict the chance of a certain outcome from recommending an article to a user, to a new user, given the article text and given the past observations you have with the article so far. Okay? So predict your next token from your previous tokens. It's an LLM. Okay? So our data for that is coming, it's this historical data set. It has many past articles and many sequences of interactions. And from this, we're going to learn, basically, by defining a class of sequence models that map the history to a prediction of the next outcome, and doing SGD. All right. So very scalable in that sense. Now, my claim, which then actually comes out rigorously in the math, is if you can do sequence prediction like this, then you must have learned to comprehend uncertainty like an optimal Bayesian person would. Okay. So why? Somehow, if I see the article text, and then I see 3 people click on the article as soon as they got it, should I pay attention to the clicks or should I not pay attention to the clicks? Should I mostly pay attention to the article text in my initial belief? In order to make predictions well, I need to be able to extract as much information as I could from the text and know how much to trust it versus the other information I've gathered. So I must be able to make conditional predictions the right way, and so somehow prediction is enough. Okay. There's no need for explicitly modeling the use. Okay. So I'm going to take that belief and just trust the sequence model. So now what do I do to make decisions? Well, within a day, I don't have as big a set of articles. I have a smaller set. I don't have all the articles from across time. I have the ones that were just released. And I don't have maybe as many observations of those articles. It's just the morning, and I maybe have only a few interactions so far. Now, I want to take my data and arrange it in a format that looks similar to the historical data, but view the problem as one of missing data. There's a lot of interactions that I could potentially have, but I haven't had yet. And my question is really, what might the future look like if I chose to recommend this article to more people and could fill in those question marks? Okay. So if you view the world that way, it looks like one of generating outcomes, generating observables. Right? And we've seen these remarkable feats of AI models generating things. So if you think of it like an LLM, There's an initial token, Z1, then there's a token, Y11, then a token, Y21, then a token, Y31. And what comes next? What's the next word? All right. So just like an LLM would, just like in that sort of autoregressive formulation, I'm going to autoregressively sample the missing entries. And just like an LLM would complete a coherent paragraph, but one that might come out with many different styles, I'm going to complete a coherent sequence of user interactions that might have many different paths. So I could complete for the first article that I think it's a great article, and I think it's going to get click, 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 click. But I might complete for that article that I think it's a bad article, and I'm going to get no click, no click, no click, no click. So I generate forward a scenario like this. And that generates a perspective, kind of an imagined perspective, on how good these articles are. Okay. So I've filled in my missing data. If I acted like it was the truth, I know everything now. So let's act like I've filled in the missing data properly. I take that table, I apply my reward function to all of the interactions I've imagined, and I have out now an imagined reward rate for each of the articles of the day. Okay? So then I go through and I look which of my handful of articles is best for this user segment under this imagined way of completing the missing entries. If there's an article that I know is bad, then no matter what, when I generate this sequence, it's going to look like it's a bad article. And it's going to have no chance of winning this. But if there's an article that might be great and I just don't have enough data on it, then I might fill out this table such that it looks great, and I might pick it as the winner. Okay. So then, I actually recommend that article. And I gather a real observation, not a fake one. I get a new table, and I do this process again. Okay. So I think this is quite exciting because it's a very different primitive than, so let's say, bandit algorithms usually look like they're using. It relies on sequence modeling and sequence generation. It doesn't make reference to latent parameters, just only makes reference to outcomes. But under the hood, it's not such a new thing. Okay. So what I actually just implemented is a well-known algorithm, which just did Thompson sampling through a different lens. Okay. And I'll explain this to you. So this is my fact one, which I said, is this new? Somehow it's hard for something that looks like that to be new. I mean, I don't know. But conceptually, I guess it's a bit new. So I'm going to define these things. HT is the history. It's everything you know up till now through the day. Now, there's a true population mean for an article, and that is the reward I would get if I showed it to the whole user segment on average. And there's a generated population mean. The generated population mean were these mu's here that I sampled forward. So the fundamental question is, when I generated these imagined means, do they have anything in relation to the real potential mean I would get if I actually did recommend the article to everybody in the population. And they do. They follow the same conditional distributions. So what I generated forward is a sample from the posterior distribution of the population mean. Okay, how could that be? Well, I have these missing entries in the table. I filled them in with the same conditional distribution as the true potential entries of the table. Okay. So the blues have the same conditional distribution as the missing black entries. And so a function of the filled in table must have the same distribution as a function of the generated table. That's the proof. All right, same proof. The action that I sampled is a sample, is drawn from the posterior distribution of the optimal action to have shown that population. For the same exact reason. It's a function of the missing data, and I filled in the missing data with the right conditional law. So I sampled an action from the conditional distribution of the optimal action. Okay. This thing is maybe the most popular multi-arm bandit algorithm, and so you might expect it to work well. But usually it's hard to implement this kind of bandit algorithm in a scalable way with neural networks and so on. And this reformulation is giving us a path to do that. I lost track of time. When, how am I doing? 4:30. Okay. So, from here, there's maybe a few things to do. This is the bulk of it. You tilt your head a little bit of a different way, and you realize that there's a way to implement something that seems to rely on kind of not scalable tools in a way that aligns better with modern machine learning practices. There's a question of how far this can really go. So far, it has imagined that I have the right sequence model. It's exactly Thompson sampling if you have exactly the right sequence model. But you don't expect to have exactly the right sequence model. So this here is a kind of a guarantee that holds even when you don't have exactly the right sequence model. This term is a normalized version of regret. It takes an average across days and then an average across users within a day. And it says, how much did my reward degrade relative to an oracle that always recommends the best article? That normalized regret is bounded by two terms, one of which decays towards 0 as you have lots of users throughout a day, as it should, because you're able to quickly learn what the best thing to do is. So this is a term from an analysis of a past life of mine that bounds the regret of Thompson sampling. This is the new thing, which I think is adding some mathematical heft to my claim that if you can model a sequence, then you really know how this world is working and you really do comprehend uncertainty properly. It takes the infinite data, or kind of population version of the sequence prediction loss, and says that if the model you're using is close to the best model, then your decision performance does not degrade very much. Okay, so somehow prediction loss actually degrades actually controls online decision performance. This is not a Thompson sampling specific thing. It applies to all algorithms and is like a data processing inequality. Okay, so can you actually do this? I think there's a question of how well you could do this in the full complexity of a modern recommender system, which is sometimes pretty crazy. But certainly you can develop academic scale implementations that really exactly work. So due to time, I'll just go very quickly through somehow what I presented before is slightly idealized. It imagines you have lots and lots of data, which we have a little less if we do some data augmentation. And it imagines you can sample out very, very far, which is a bit wasteful. So our practical implementations don't sample out so far and do some bootstrapping to expand the data set. I can talk about this offline. So I'll just go through quickly that we run two kinds of experiments. One is synthetic and shows that really you could, on some small scale, train a neural network and do exact posterior inference this way. Okay. So first is a plot of regret. Red is, so this is regret in a case where your prior is some kind of mixture distribution. Red does kind of exact implementation, costly, of Bayes' rule to do Thompson sampling. Blue does sequence modeling and autoregressive generation with a neural network. It's exactly the same. Up here you have kind of the use of a bad computationally convenient prior. So you can see there's some cost to just making approximations rather than going through the neural network. And these other things are the kind of stuff you often see in the literature. So like Brown is UCB, theory-inspired UCB. Okay. Another kind of thing here is coverage. So I claimed that the autoregressively generated mean looks like a posterior sample of the article's possible mean. Right? It's a projection of how good the article might be. These plots say that that projection is perfectly calibrated. So this calibration mean, the 20th to 80th percentile range of those autoregressively generated samples contain the truth 60% of the time. It actually worked. And maybe unsurprisingly, these kind of things that use approximate priors are not calibrated. Right? They're way off. Okay. The last thing, we're going to take this Microsoft News data set, which has, by industrial scale, really not a lot of articles, but something like 10,000 articles for us to play with, and headlines of those articles, and click data. We're going to integrate an LLM with the interaction data to build a kind of a baby sequence model and see if we can get this working. Okay. So in blue, we have the exact algorithm, basically, is this approximation of the algorithm that I showed you before. This is its regret. In red, we have sort of the same thing, but we've hard-coded a kind of Bayes rule into it. Okay, and again, even in this more complex setting, the autoregressive forward samples are perfectly calibrated. So we've managed to get this kind of calibrated quantification of uncertainty in an action's forward-looking performance through sequence modeling. And it so far is really working. Okay. I guess this last bit is just pointing out that there's been a lot of work that's gone into trying to get this kind of uncertainty quantification, like epistemic uncertainty quantification with neural networks. It's finicky, right? So one of the best methods so far is something called ensembling, and usually the complaint is that that's computationally expensive. In our setting, if you directly apply that, it really doesn't work. That doesn't mean that it can't be made to work, but it shows the subtleties of things. Okay. So thank you here. I don't have much time for questions, but I'll take what I can.
Thank you. Any questions from the audience?
Thank you very much. It's a wonderful talk. So it's very, very interesting. So I was wondering, like, since you're talking about large language models, so is this kind of a Bayesian setup related to the, actually remind me of the recent studies on this in-context learning for language models, actually? So the way they view it, or like the way they analyze it, is exactly the same thing. It's like if you can predict the next token, or like you can do the sequence generation very well, you can essentially implicitly learn the context or the concept in that case, so that you can generalize to the, let's say, a new task or like a new sequence. So it seems like to me this Bayesian perspective seems to be very related to what you are exactly proposing here, is that they can show actually this kind of sequence modeling can essentially implement posterior sampling or like this Bayesian regret approach. So I was wondering, can you comment on that? Is there a connection to that thing?
Yeah, I mean, it depends a little on which one of these papers you're referencing, because they differ in how close they are. I think it's true that somehow definitionally, in-context learning, it's conditional inference. You know, you condition on the prompt. And so it's definitely sort of Bayesian. I think that it's also, I guess you can see from this that if you apply it the right way, it can be exactly, implementing posterior inference. Yeah, the question of recovering the concept.
Like your U there, which is latent, but they don't explicitly do that because you can estimate the posterior distribution through pre-training very well. So that's why you can implement that posterior.
Right, I think that's right.
All right, thank you. That's very nice.
Okay, I think we're out of time, so let's thank the speaker once again.